Okay, so hello and welcome to today's webinar. I suppose we'll get started. So today's webinar is alternatives to power. Today we'll be discussing sample size determination using methods or metrics other than power. So my own name is Brian Fox. I'm a research statistician here at Enquiry, and I'll be your host for this webinar. So I'll just quickly go through the agenda for today. I will begin by discussing statistical power and how it's used in the sample size determination process. I will then give a brief overview of some of the alternatives to using power for sample size determination. Then we will focus in more closely on some of these alternatives. Firstly, we will take a look at statistical intervals in the form of confidence intervals and Bayesian credible intervals. I will discuss what these are and how they are employed in the sample size determination process. I will then give a closer look at some of these methods within our software, which is called Enquiry. Just to show some of the features of these methods. Note that I will be referring to a lot of Bayesian ideas in this section, but I will be giving a more formal overview of these ideas and methods in the next section, section 3, where I will discuss the general idea of using a Bayesian framework for sample size determination and some of the methods available in this area. Then, similarly to before, we will focus in on two areas in particular, these being Bayesian assurance and the Bayesian posterior error method. And then we will return to Enquiry and show a detailed example of the posterior error method in action. Finally, I will conclude with just a brief discussion and conclusion, where I will highlight some of the points made during the webinar. And I should mention that I will aim to conclude the webinar well within an hour or so. Note that if you have any technical difficulties, then feel free to get in contact, and we'll hopefully be able to help you resolve these. Also, I will try to leave time at the end of the webinar for questions. The questions that come in through the course of the webinar. Depending on time, I may not get to all of these, but I will make sure to reply to any questions that do come through by email after the webinar concludes. Also, I suppose if any questions or ideas occur to you after the webinar concludes, then I will be sharing the relevant contact details if you want to get in touch with us at the end of the webinar. And also, I should mention that today's webinar is being recorded, and a link to it, along with the slides for this presentation, will be sent out to you after the webinar concludes. Okay, so as many of you have probably heard us mention before, Enquiry is widely regarded as being a cost-effective and easy-to-use trial design platform, which can be an essential tool in optimizing your clinical trial. Enquiry is known as the complete trial design platform to make clinical trials faster, less costly, and more successful. And Enquiry is one of the most widely used sample size and power calculation softwares available, and has been on the market for over 25 years. So Enquiry is essentially split into 4 different tiers. The first being our basic or core product, which has a vast array of different sample size and power calculation methods for many different types of hypotheses and hypothesis types. And then our next tier is Plus, which includes all the methods from the basic tier, in addition to our Bayesian methods, a lot of which we'll be seeing today. Then our next tier is our Pro tier, which contains basically all of our adaptive designs and methods, like group sequential designs, for example, and also our interim monitoring tools for these group sequential designs. And then finally, we have our Expert tier, which includes our milestone prediction tool for both normal enrollment and also survival or time to event targets. Okay. So now let's finally get into the statistical part of today's webinar and take a look at sample size determination using power and some of its alternatives. So sample size determination, well, what is it? So it's just the process by which an appropriate sample size is found for a study. This is obviously a major part of the clinical trial design process. Essentially, we are concerned with determining the minimum sample size which can satisfy certain criteria, whether this be power, given interval width, enough to address safety concerns or costs, etc. And we want the sample size to be as low as possible while still satisfying these criteria for a multitude of reasons. One major reason for wanting your sample size to be minimized is cost. Obviously, companies don't have infinite resources and can't afford to enroll millions of patients in every trial in most cases. Also, there may not be a large amount of patients to draw from, as is often the case with rare diseases, for example. In addition, there are often ethical concerns where a balance has to be struck between enrolling enough patients to ensure a drug or a treatment has shown efficacy and safety, while not delaying the trial for a very large amount of time in order to enroll this large number of patients, because this would delay patients from receiving a drug or treatment who may desperately need it. Also, I suppose enrolling a large amount of patients in a trial unnecessarily may result in resources not being able to be allocated to other drugs or treatments, which may be more promising, for example. So therefore, sample size determination is an extremely important part of the trial design process. And the metric or metrics by which we determine the sample size should be very carefully considered. So power is by far the most common metric by which to determine the sample size. Power is defined as the probability of rejecting the null hypothesis when it is indeed false. Therefore, it's the probability of detecting a true treatment effect of a specified size. And as such, the sample size for the trial will be calculated so as to meet a minimum level of power. So despite being the most common metric for sample size determination, power does not come without any issues. In order to calculate the power or sample size with power, one must specify the value for the effect size and also various other parameters in many cases, like the variance, for example. And obviously, it's usually impossible to know what these values for these parameters are with absolute certainty before the trial, and so estimates have to be used. So this brings forth the main issue encountered in using power as your sample size determination metric, and that is that the calculated sample size will only result in the study achieving the target power if the assumptions made in the power calculation are indeed correct. This means that if deviations from these assumptions are encountered, the trial may be under or overpowered, resulting in either the trial being unable to conclude for efficacy, where a potentially true clinically relevant treatment effect is indeed present, or in wasting resources on the trial unnecessarily. So using alternative metrics to power may help alleviate this issue, and that's essentially what we'll be discussing today. Also, using alternative metrics might get around the kind of dichotomous nature of power, since it's basically heavily based upon hypothesis testing. Okay, so what are the alternatives to power? Well, one of the main alternatives to power is to use intervals. This kind of ties into the whole idea of precision-based estimates. So instead of finding the sample size to give a minimum level of power, you're instead calculating the sample size, which ensures a certain criteria is satisfied for a given interval width. For example, for a confidence interval, the sample size is calculated in order to ensure a certain level of confidence, usually 95%, that the parameter from the population of interest lies in the confidence interval. And indeed, there are many who would be strong proponents of this idea. A paper from 2018 by Rothman and Greenland discusses this idea of using precision rather than power for sample size determination. and I would definitely recommend taking a look at this should you wish to learn more. Okay, so some common intervals that are used in practice would be confidence intervals, prediction intervals, Bayesian credible intervals, and mixed Bayesian likelihood intervals. So Bayesian methods are also very attractive when it comes to combating the issues associated with power. These methods can largely be split into two categories, the first being hybrid Bayesian methods, and the second being fully or pure Bayesian methods. So hybrid Bayesian methods integrate Bayesian methods into existing sample size determination designs in order to provide greater context about the uncertainty surrounding population parameters. A very common example would be mixed Bayesian likelihood intervals, the posterior error method, Bayesian assurance, predictive power, and many others. I should note that we will be discussing mixed Bayesian likelihood intervals, the posterior error method, and Bayesian assurance in a lot more detail later in the webinar, just for anyone interested. So pure Bayesian methods then, on the other hand, calculate the sample size based solely on a Bayesian metric. The most common methods here would be Bayes factors, credible intervals, the continual reassessment method, and Bayesian utility or cost functions. So we will be examining credible intervals out of these later in the webinar. Okay, so now let's finally take a look at some statistical intervals. So from a frequentist perspective, the most common interval by far would be the confidence interval, although there are also like tolerance intervals and a few more. So I touched on it previously, but the confidence interval is just a range of values for a parameter of interest from a population, which is expected to contain the true value with a specified degree of confidence. From a Bayesian perspective then, the most common type of interval would be a credible interval. And credible intervals are essentially just intervals which contain a specified amount of the posterior distribution for the parameter of interest. For example, a 95% confidence interval, credible interval, contains 95% of the posterior probability, which is to say that there's a 95% chance that the true value is in the interval. And I should mention here, for anyone who might not be familiar with the idea of a posterior distribution, I will be talking about this in quite a bit more detail later in the webinar. So with the credible interval, the unknown parameter is a random variable and the bounds of the interval are fixed. Whereas with confidence intervals, you kind of treat the unknown parameter as being fixed, and then the bounds are instead the random variables. So in this way, we can kind of think of credible intervals as being the Bayesian analog to confidence intervals. And one can see why that might be quite an attractive choice, since they're not only allowing you to incorporate prior knowledge into the method, but also like as long as any of the assumptions made hold, then the credible interval can be interpreted as the probability that the true population parameter is in the interval. So like often people assume that confidence intervals have this interpretation, but obviously that's not correct, as confidence intervals are intervals under the frequentist paradigm. So under repeated sampling, 95% of the confidence intervals created in the same way are expected to include the true value. So maybe less intuitive, less of a kind of nice property. Okay, so I'm going to assume that everyone here is familiar with the basic idea of constructing a confidence interval, but how do we conduct or construct a credible interval? Well, here we just have some of the methods put forward by Adcock from 1988 in that paper, and also from paper from 1997 by Joseph and Benlisley, which is probably the main one that I'll be talking about in the following slides. So Joseph and Benlisley focused on the normal means case and allowed uncertainty to be built into the variance estimate. So essentially you may use prior information about the expected mean and variance, And note also they refer to precision in their paper, which is basically just 1 over the variance, just in case that was confusing for anyone. So when it comes to the actual interval construction, and hence our sample size determination afterwards, the process does become a bit more complicated than it would for a similar confidence interval. Essentially, we'll be considering here anyway, 3 of the most common criteria for sample size and 3 testing scenarios which are based on the prior information available and the type of final analysis that we want to conduct. So our 3 criteria for our selection criteria are going to be the average coverage criterion, or ACC, or average length criterion, ALC, and worst outcome criterion, WOC. So ACC assumes the length of the credible interval to be fixed and ensures that on average, the coverage of the posterior probability will be at least what you say it is, 95%, for example. So like for example, you may specify a 5% coverage error and a length of 0.1. So then your length is fixed at 0.1, and on average, the coverage is at least 95%. So this is what was originally proposed by Adcock, and then Joseph and Bellesley introduced the average length criterion, which is essentially the inverse of the average coverage criterion. So now we have a fixed coverage, and on average, our interval length will be at most equal to your specified value. Finally, there is the worst outcome criterion, which is an extension of the average length criterion, which goes beyond just the on average part of that criteria. For example, with the average length criterion, there will still be a 50% chance that the average length will be slightly larger than your specified value. But with the worst outcome criterion, you can specify a cutoff, 80%, for example. And then for a fixed coverage probability, the length that, the probability that the length is at most what you have specified is 80%. So, it is slightly confusing, I suppose, this kind of idea, but it will hopefully make a bit more sense when we take a look at the worked example in just a moment. But essentially, it can kind of be thought of in a similar way to the coverage probability adjustment in a confidence interval. If you do want to learn more with any of these criteria, I would definitely recommend taking a look at the Joseph and Bellesley paper. Okay, so now for the estimation methodologies. The first case is where your precision is known, which is a relatively straightforward extension of the frequentist scenario, except that you would subtract the size of the prior that is used to find the known precision. And once again, I'll be discussing this later if people aren't too familiar with that. Then we have the unknown precision case, which is where you specify a prior distribution for the precision. And then finally, we have a different type of interval, which is a mixed Bayesian likelihood interval. And this is an interesting approach, which combines the desirable kind of credible interval characteristics with the final analysis of a confidence interval. So you have to fulfill the Bayesian credible interval criteria, where the interval contains a certain proportion of the posterior probability. And then also it must fulfill the frequentist confidence interval criteria, where you were to construct a large number of these mixed Bayesian likelihood intervals in the same way, then 95% of them are expected to contain the true value. So this final method is useful for those who may still be required to use a confidence interval for the final analysis, since it's the industry standard in some ways, I suppose. But they may still want the benefits of being able to incorporate prior data. I should mention actually that inquiry does currently have a wide range of credible interval and mixed Bayesian likelihood interval methods available, both for like mean and proportions cases and the 1-2 group cases. just in case anyone's interested. So yeah, so now let's take a look at how we actually conduct a sample size calculation for these methods. So I would expect a lot of you to maybe be familiar with this formula on the top up here, which is just for the normal means case when the variance is known. And for confidence intervals, the majority of endpoints have very easy to use and simple kind of sample size formulae. But then for the credible interval case, the formula chosen depends not just on the endpoint and the number of groups, etc., but also on the choice of selection criteria and estimation methodology that we discussed previously. So as a result, the formula for the sample size determination can be quite complex, and this may be seen as a barrier to the adoption of these methods by some. But in certain cases, the formula required can be actually rather simple, as is the case for the formulae shown here. So on the left, this is the known precision case where the same formula actually applies to all three selection criteria. And then on the right is the unknown precision case where the average coverage criterion is chosen. And average coverage criterion was chosen just because it was the simplest out of the three criteria formula for those three criteria. And these formula are all taken just from the paper by Joseph and Bellesley, where the precision is assumed to be gamma distributed, and I suppose actually also N0 here. I should probably explain that. That's just the hyperparameter, and I'll be talking about that a lot more in just a moment. Okay, so yeah, now let's finally take a look at these within Enquiry with some worked examples. So this is just an example for the one normal means case, which is actually from the 1997 Joseph and Bellesley paper. We will be using Enquiry, obviously, in order to replicate example 2 here. So this one here. And we're going to be using gamma distribution as per the paper, with a shape parameter of 2 and a rate parameter of 2, which is essentially the prior distribution of the precision. We have a hyperparameter of 10, which is essentially the prior study sample size, or alternatively, you can think of it as the size of the study that would have been used to obtain the information about the mean and precision. The interval length is 0.2, which is going to be the length of our credible interval or our mixed Bayesian likelihood interval. And then the coverage probability is 0.95 or 95%. Okay. And then we are also given the sample sizes here. So this 385 is the frequentist confidence interval sample size. Then we have our 3 criterion, where the 95% after the worst outcome criterion is just the coverage probability. Okay. Or sorry, the 95% here just implies that the probability that the actual length of the interval will be less than or equal to the specified length for fixed coverage, and that will be the case in 95% of the actual cases. Sorry, yeah, that's my mistake. Okay, so now let's take a look at this in Enquiry. So when you first open Enquiry, this is what you'll be met with. So we have 4 different quadrants here. This home tab is what you'll probably be using most of the time. I'll just assume that most people aren't too familiar with Enquiry and quickly go through how to use it before we get into our actual example. So basically these 4 different icons, these 2 on the right, the prediction relates to our expert product, so most people don't need to worry about that. This is just our randomization list tool, which can be used. And then you can also open any existing Enquiry files, which are also shown on the right here, your recent files there. And then you can access help and support, and you can also see what packages you have activated. But for us, in our example, what we're mainly interested in is this here, which is our new table button. You can also access it here with the Control N on the keyboard, or through that icon there. Okay. So if we go in here, what we are interested in today is a confidence interval for one mean using the normal distribution. Okay, so let's go back and actually take a look at what we're going to be replicating. We're going to be looking to replicate the frequentist confidence interval of 385. So I suppose our confidence level here is going to be 0.95 as per the example. We have a two-sided interval. Our standard deviation is going to be 1, and I'll talk about why that's the case in just a moment. It's basically due to the way the gamma distribution, due to the way the standard deviation is calculated through the gamma distribution for our for the precision. And then the distance from the mean to the limit is basically going to be half the interval length, which in our case, our interval length was 0.2, so it's going to be 0.1. And we can see that our sample size does indeed turn out to be 385 as per the example. So just to explain how this all works in inquiry a little bit more. So basically what I've been doing there is I've been entering in parameters in what we like to call the main table, which is this area up here, this kind of Excel type interface. So each of these columns essentially refers to sample size or distance to the mean limit calculation. So those rows are highlighted in yellow since they are what we like to call solver rows, i.e. they are rows that we can be solved for. And you can also select this from the dropdown, and that will specifically show you what's required, where some of the parameters in white will be required in order to calculate your distance to mean to the limit. Okay, so then once the calculation concludes, you'll get an output statement, and then also on the right here, as you click through these parameters, you'll see there's a help window on the right, which will give you a little synopsis of the parameter itself. Usually it will give a suggestion also of what to put in for that parameter, and then also a list of the acceptable entries. Also, in this little button here, we have our Home tab, which is essentially a synopsis of how to use the table. In many cases, this is actually quite a bit longer. This is one of our earlier tables. And then also we have our references that might be of interest. Okay, so yeah, hopefully that gives you some idea of how tables actually work in inquiry. You can see it's not really too complicated. Like this is a relatively simple example. But now let's take a look at our credible interval example, which is going to be done using this table here. And in fact, I'll open up a new one just so you can see. I have it filled in already just for the sake of time, but just to show you how it's done, I'll quickly go through and explain how to do this. So in our example, we're going to be using the average coverage criterion, which is just the default here. We're going to have coverage probability, which is coverage error, which is 1 minus coverage probability of 0.05. So that's just the probability that the true mean is outside of the interval, and we can interpret it that way just due to the Bayesian framework. So nu and beta here are just the shape and rate parameters for the precision, or the prior distribution of the precision. So which, just once again, is 1 over the variance. So both of these were 2. And in the gamma distribution, the mean will be nu over beta, and the variance will be 1 over beta squared. So if the parameters are the same as they are here, then we'll have a mean of 1, and the variance will decrease as the parameters get larger. So, the variance will be half here, or sorry, 1, which is quite a wide distribution, and so not very informative as far as precision estimates go. So the interval length is going to be 0.2, and the hyperparameter is going to be 10, which is quite small, must be said, which is perhaps reflective of how uninformative our prior was. And then the subset parameter here is only required for the worst outcome criterion, So we can leave that blank. And once I enter in or click out of this cell, you can see our sample size is calculated at 761, which is what we expected as per the example here. Okay, so yeah, so now let's take a look at what if we use the average length criterion or the worst outcome criterion. So we'll copy over our values here, and the default subset value is 0.5, which is why this ran there. So you can see that the worst outcome criterion does have by far the largest sample size. And that's to be expected, I suppose, since we have far stricter criteria here. And since our subset is only 0.05, that means that we only have a 5% chance that the resulting interval length will be larger than our stated length of 0.2. Also here you can see that the average coverage criterion has a slightly larger sample size than the average length criterion. Note that this isn't always the case. One can be larger than the other. Sometimes they can be lower than the frequentist sample size, which I know is kind of hard to expect, seeing as it's only 385 here. But in some cases, they can be a bit lower. So yeah. So let's explore what would happen if we increased the gamma parameters, I suppose. Since essentially, as I mentioned, the higher these are, the kind of more confident we're about our estimate for the precision. And so we should see that the sample size should decrease. If I set both these to be quite a bit taller, or sorry, larger, then yeah, we see it does decrease. And that would be the case across the board here. But then let's see what happens if we set these to a very, very large value, so like 1,000, and we can see that this looks very, very close to our frequentist sample size. And that's basically because we're so sure of our estimate that we've effectively reduced it to the state where it's just our hyperparameter, which is essentially the sample size of the kind of prior study, if you want to think about it in those terms. So 375 plus our hyperparameter of 10, and that's going to be equal to our frequentist sample size. So hopefully that gives you an idea. Like essentially what this is implying is that we have a very narrow distribution for the prior distribution. Okay, so yeah. Now let's just take a quick look at a mixed Bayesian likelihood example. I've just pre-filled this one since you can see that most of these parameters here are all the same as before. So the main difference here is just that we no longer have a hyperparameter, since it's now a frequentist analysis that we'll be conducting, and we're not going to be making inferences based on the prior. So this method here uses simulation. So we have a specified seed of 1,000 for each of the calculations here, which is just to ensure reproducibility. So now all we have to do is enter in the number of simulations. We'll just set them to be quite high. So 10,000. And we can see that there are very slight sample size increases for all the cases here when compared to the credible interval. However, they are quite similar. You can see relatively similar. And this is because our hyperparameter was very small in the previous example. So, they're obviously also actually very similar to our expected values based on, my apologies, based on this table here. So you can see 771, 606, 2175. However, I'll say they're not the exact same, since this is a simulation-based table. Okay, so I suppose just before we move on, one very common criticism of these methods is that the average coverage criterion and the average length criterion can give very similar sample sizes in some cases, and it's not always clear which one we should use. Our recommendation is just to consider what you are concerned about for your own trial. So are you more concerned about the length of the interval or the coverage probability and maintaining those? Okay, so yeah, now let's start to move on, just in the interest of time. And let's take a look at Bayesian testing. So I know I've kind of touched on a lot of Bayesian ideas already, but now I just want to go into a bit more depth on Bayesian analysis before we go any further. So Bayesian analysis can be used to combine existing knowledge, expert opinions, and real-world data in order to make inferences. So this can be done due to the fact that under the Bayesian interpretation of probability, you must express a prior belief in an event, and then this belief can change how new information, as new information becomes available. So this means that the parameters that we wish to estimate are seen as random variables, and we're going to determine what's going on through a posterior distribution for the parameter of interest, which we've already come across in our credible interval discussion. So this is a large departure from the frequentist framework, where parameters are seen as a fixed constant, not random variables. And so the observed data is then viewed as a repeatable random sample. So, under the frequentist interpretation of probability, probability is based on the frequency of an outcome after a large number of random events or observations. Okay, so I've mentioned that we want to estimate a posterior distribution of a parameter, and the posterior comes from a prior distribution and the observed data. So the prior distribution of the parameter is based on our existing knowledge of that parameter, and so it is independent of the observed data. And the prior can be derived from historical data or experience, like other trials in a similar area, for example, or from pilot studies or published research, in fact. Or it can also come from expert's opinion. As you know, there's many different sources. And then choosing this prior is a major part of the Bayesian analysis, but it is a bit of an issue for some. So some believe that the prior is a major barrier to people who want to adopt these kind of methods. So, the common priors can be very flexible, and so maybe open to, inclusion of bias or, a bit of abuse in some ways. But by and large, usually what someone will do is use a very flexible distribution, like a gamma or beta distribution, or, in fact, a lot of people do use the uniform distribution, which obviously implies that the parameter can take any value in the available range with equal probability. And so this is then known as an uninformative prior, and so it's a bit kind of safer in that respect. Okay, and then finally, we combine this prior with our observed data, and then we get our posterior distribution. And then that's what we'll be using to make inferences. Note that, prior studies, just before I move on, I suppose it's worth noting that prior studies does seem to be the gold standard when it comes to determining your prior, and data can even be used from your phase 2 trial in some cases. And this is discussed, extensively in a lot of our previous webinars, if you want to learn any more about that. And they're all available on our website. Okay, so this is, all of these ideas are very much underpinned by Bayes' theorem, shown on the top right here. And here, theta is our parameter of interest, and then d is our observed data. So here we have the posterior distribution of theta given the data d. For example, we might have the null hypothesis of theta equal to 0, and then this would be the probability that the null is true given the data that has been observed. And then this is equal to the probability of d given theta, which is the likelihood of getting the observed data given the value of the parameter theta. which is then multiplied by the prior distribution for the parameter. And then this is all divided by the marginal distribution of the data or the evidence. Okay, so then finally, before we move on the right down here, you can see we have a visual representation of this idea. So the prior here is in black, and then the likelihood is blue, and the resulting posterior distribution is shown in red, where you can see that the prior has been shifted to the right by the observed evidence. Okay, so now that we're kind of familiar with Bayesian statistics, how can we use them in order to calculate a sample size? So, as mentioned, previously, there are two main categories for Bayesian statistics for sample size. The first is sample size determination for Bayesian methods, and the second is improving existing sample size determination methods with Bayesian methods. So, sample size for purely Bayesian methods is where Bayesian parameters are going to be the subject of our analysis. And as such, we pre-specify what success is for these criteria, and then use methods such as those shown here in order to derive a posterior distribution for these parameters, and then conduct our sample size determination based on this posterior distribution. And then we have our hybrid Bayesian frequentist methods, and these are for when you're planning to do a frequentist analysis, but you wish to incorporate Bayesian methods into the design to provide greater context about your parameter uncertainty. For example, where you're conducting a t-test, but you want to tackle greater uncertainty in the variance parameter. So, this idea can give a trialist, a bit more scope about the different metrics for how likely a frequentist analysis is to succeed, or it can just give us additional, alternative criteria for what success actually means. Okay, so just because it's a very popular method in this area, or a very popular Bayesian method, I'm going to quickly touch on Bayesian assurance. But as mentioned, I won't be doing an actual example in inquiry here. So Bayesian assurance is one of the most commonly used and powerful hybrid Bayesian frequentist methods. And so I'll quickly touch just on it here and explain its use in sample size determination. So Bayesian assurance is the unconditional probability that the trial has a successful outcome, and we arrive at this probability by assigning a distribution to one or more of the parameters that would otherwise have been point estimates. For example, instead of just saying the effect size is 30%, you may say that it follows a normal distribution with mean 30% and a certain variance. Then the assurance is calculated as an expected power weighted over all possible values for the effect size. So what a parameter is like the variance could be a prior, for example, or be assigned a prior, I should say. So this can be sort of seen as a formalized sensitivity analysis, where instead of just focusing on our estimate for the effect size, we instead cover the range of possible effect sizes and then weight these by how likely it is they will occur. And as such, assurance is often thought of as being a better representation of the true probability of success. For a visual representation of this, on the right here, you can see the power is represented by the solid black line, where the x-axis represents the effect size. And so as the effect size increases, the power increases, and that's assuming positive effects are better. And then the dotted line represents the density of the prior for the parameters you wish to represent with a distribution. So then we will take the product of these two curves and integrate over all possible values to get our assurance. And then this is then what's used with our existing frequentist sample size determination method. So note that what I have shown here is assurance for the power. However, it is a very broad concept and far broader than just power. So you can actually calculate the assurance for whatever metric you have chosen for your trial success. just to note that here. Okay, so here I've just included some examples of assurance calculations, just taken from a 2005 O'Hagan paper. And, here power is just denoted by phi or pi, is defined as a function of theta. And then this theta is a vector of parameter values that you wish to consider. So this may be one-dimensional, or there may be multiple parameters. So then the power is the probability of rejecting the null given these values, which is to say that it's a conditional probability. Whereas the assurance, shown here as A, is the unconditional probability of rejecting the null, which is calculated as the expected value of the power over all the values of the parameter theta. So then I just included some calculation methods here, but I won't go into any detail on those. So now let's finally take a look at the posterior error approach. So under the frequentist framework to hypothesis testing, we use null hypothesis significance testing and p-values in order to test our hypotheses. So we know that p-values are often misinterpreted. So the p-value is the probability of observing the data that has occurred, or more extreme, given that the null hypothesis is true. So if this is sufficiently small, then we get a significant result and may reject the null hypothesis. And then similarly, the type 2 or beta error is probability of not rejecting the null hypothesis when the null hypothesis is true. So a natural question is, does this framework actually reflect accurate decision making? So Bayesians like to think of this problem the other way around, and then this is known as the inverse conditional problem. So instead of the probability of getting this data given the null is true, they instead ask, what is the probability that the null is true given this data? So from a researcher's point of view, you can understand that this outlook does make a lot more sense. And this is an ongoing debate. There's definitely fors and against. So the approach put forward in the 2000 paper by Lee and Zelen aims to solve the inverse conditional issue by essentially converting the frequentist test significance level and power into what they describe as the Bayesian posterior errors. So these type 1 and type 2 posterior error rates give the probability that the null hypothesis is true given the result is significant, and also the probability that the null is false given the result is not significant, respectively. Okay, so what we end up with is a hybrid approach where the outcome of interest, what we would call success, is still defined in terms of the p-value, and we find the posterior probability that the null is true given a successful frequentist result. So Lee and Zelen give formula to calculate the appropriate frequentist alpha and beta values to achieve the desired posterior error rates, given a prior probability that the null hypothesis is not true. So you only need to specify this prior probability that the null hypothesis isn't true in order to conduct these types of calculations. Okay, so in order to explore this method, we'll just first set up a very simple two-group t-test example, and then we will go into explore what would have happened if we used Bayesian posterior errors in the analysis. Okay, so now let's go into inquiry, and we'll be using this table here. So we're going to assume a significance level of 0.5. We have a two-sided analysis. We don't need to worry about the individual group means. We're going to have a difference in means of 2.6. Since this is all that's used in the calculation of the effect size, we don't actually need the individual group means. And we have a standard deviation for both groups of 10.6. Then, once we enter in our power of 80, we see that we get a sample size per group of 262, which is what we expected based on this example here. So now let's have a look at what would have happened if we were using the posterior error method. So we'll be using this table here. I've just pre-filled many of these parameters since they're the same as our frequentist parameters, except that now we can have per group standard deviations rather than a common standard deviation. So also note actually that we will be using the z-test here rather than the t-test, but for the sort of sample sizes we're looking at, i.e. in the region of 2 to 300, this isn't expected to make very much of a difference. Okay, so we're going to be specifying our posterior false negative and false positive errors here. And this is slightly confusing as under the frequentist framework, alpha refers to the false positive error rate, which is the probability that the null is true given that it is rejected. And then beta refers to the false negative result, which is the probability that the null is not true given that it was not rejected. So under the Lee and Zelen approach, we're going to denote our false negative error rate by alpha star. Excuse me. And then beta star is going to be our false positive result. And as such, commonly used values for alpha and beta star are 0.2 and 0.05. Respectively, which is similar to 80% power and 0.05 significance level that one might expect from a frequentist design. Okay, so now let's enter in our alpha and beta stars. And then we are asked for our prior probability against the null hypothesis. So here I believe we're setting this to 0.5, which is essentially saying that we don't have any evidence for or against the null hypothesis prior to the study. Okay, so if we enter in those, we can see that our calculated sample size per group is very similar to the frequentist case, so not a major departure. So yeah. Now let's have a look at what would have happened if our posterior false negative, posterior false positive error rates were the same, but that we had a 25% prior probability against the null hypothesis, which is to say that we're more confident that the null hypothesis isn't true prior to the study starting. And then what we should see is that this will result in a reduction in the sample size, and we do. Whereas if we had less evidence against the null hypothesis prior to the study starting, so let's set it to 0.75, we should see that we get a slightly larger sample size, which indeed we do. And so you can see that for each of these calculations, we also get back our significance level and power, which you would have gotten from a frequentist, which is essentially being passed through to the frequentist sample size calculation. So if we were to get these significance level and power values and pass them through equivalent frequentist calculation, these are the values that you would expect to get back. And so this kind of shows the general method of how posterior error rate method works. And it can actually be also accessed through our assistance menu here, where we have a posterior error rate calculator. And if you enter in 3 of any of these 5 parameters, then the final two will be calculated. So if I enter in, say we want to solve for the power and posterior false positive error rate, then we can do that. And you can see that this just kind of shows the ease with which this method could be adapted, and how natural a progression it is into the frequentist framework after this point. Okay, so I think that just about wraps up that example. So yeah, sorry, this is just showing what we essentially went through there, where we set our alpha star and beta star to 0.2 and 0.05 respectively, and we explored the effect that it had on the sample size, the significance level, and the power. Okay, so yeah, hopefully that was a bit of an introduction into that method. I know that I was going relatively quickly, but we do have more resources available on our website if you want to learn more about these, or do feel free to get in contact. But now we'll just finish up with a brief discussion and conclusion. So, as mentioned, power is still by far the most common metric for sample size determination, but it does have a lot of issues with it, in particular around parameter uncertainty and the effect this can have on the resulting power, and then also in terms of defining what success actually is, since it's a very dichotomous result based on the kind of hypothesis testing kind of framework that power has come from. So statistical intervals can provide a very appealing alternative to power for sample size determination, but indeed it does run into a lot of similar issues in that it has some underlying assumptions that have to be made. And then finally, Bayesian methods do have a lot of benefits and are kind of a natural kind of step in terms of solving some of the issues that we've discussed. And some of the most common ones would be like assurance, space factors, mixed Bayesian likelihood intervals. And many of these can be used to not just fulfill the Bayesian criteria, but also maybe satisfy a lot of the frequentist criteria, like posterior error method, for example, which provides a very kind of intuitive idea of what success actually is and allows you to introduce your prior knowledge about what about the null hypothesis at the design stage. Okay, so I suppose sensitivity analysis, it should also be mentioned, can be used to tackle some of the uncertainty around parameters like the variance, but Bayesian methods maybe are seen to lend themselves more naturally to that area. So I suppose in conclusion, power is very likely to remain the primary metric for sample size determination, as you know, really there is no perfect solution. All methods have some issues with them. However, a lot of these other methods that have been shown here today do provide very attractive alternatives, particularly where uncertainty in parameter estimates may be of particular importance. Okay, so if you do want to take a look at anything that you've seen here today, do feel free to go to statsolves.com/enquiry-trial and you'll get a free trial of the software. But yeah, I think that just about wraps it up for me. These are the relevant contact details, so info@statsolves.com if you have any questions. And I do see one question did come in. It was, is using a confidence interval not going to run into similar issues to power with regards to dependence upon assumptions? So yeah, that's a very good question. Yeah, and it is true. I suppose I touched on it very slightly there, but a confidence interval for sample size determination does come with a similar set of issues to those of using power. This is because you're essentially making kind of similar assumptions about the effect size and variance when specifying the interval width. So essentially, planning the sample size requires an input about some information that the study itself is intended to give information upon. And you know, these inputs are needed regardless of whether one is computing a study sample size based on power or on precision. And you know, that's why it's kind of really seen as good practice to conduct a sensitivity analysis just in order to evaluate the sensitivity of results to uncertainty about those values, not just for the case where power is used, but also maybe where confidence intervals are used. But I suppose just like confidence intervals, or indeed any precision-based metric, might have a small advantage over power in that they don't have the same hypothesis testing kind of drawbacks, you know, of dichotomizing the study results into, you know, two qualitative categories, which, you know, can have the issue of misinterpreting non-significant findings as support for the null hypothesis, or indeed in misinterpreting small, precise, significant findings to be strong evidence against the null hypothesis. Okay, so I'm just conscious I'm going a little bit over time. If I didn't get to anyone's question, I'll make sure to reply after this webinar. Thanks again, everyone, for listening. I know that was quite long, and hopefully you found it useful. But yeah, thanks again. Bye bye.